Hello everyone, let us continue our discussion on system modeling. This time we'll consider autotransformers. Autotransformers are just transformers with one continuous winding, such as shown here. Uh, we have uh, NP as the number of turns, total number of turns, and then when the winding is impressed with the voltage Vp, current Ip will flow, producing the flux in the iron core and inducing a voltage in the winding on the primary side equal to E sub P. Now, for the autotransformer, we can have a tap anywhere along this point and this point. And this tap will serve as our secondary terminals. For example, we have a tap here where the total number of turns at the secondary side from this reference or point is Ns. And because of the magnetic flux produced by the winding, uh, an induced voltage at the secondary will be equal to E sub S. Now, if the secondary circuit is connected to a load, then Is will flow and current will circulate and power is delivered. So with this, the transformation ratio is again defined as the induced voltage in the primary side E sub P over E sub S, or this is equal to in sub P over N sub S. And practically, the transformation ratio can just be obtained by dividing the primary voltage terminal Vp over the secondary terminal voltage V sub S, which are commonly given. And also, our transformation ratio A can also be equal to the secondary current Is over I sub P. And again, the field winding strength at the primary, which is the ampere turns, with equal to in sub P times IP, this will be also equal to the secondary field strength NSIS. And for the capacity of the autotransformer in kVA can just be found by multiplying the primary voltage Vp times the primary current Ip, or we can use the secondary voltage V sub S times the secondary current I sub S. Now, a two-winding transformer can also be connected as autotransformer as long as we observe the polarity of the two transformers, such as this, where this point is of the same polarity as this end. So this serves as our primary with Vp and number of turns Np, and current flowing here is Ip. Then we have the secondary with the total number of turns equal to Ns and terminal voltage V sub S and the current I sub S. Now this two-winding single-phase transformer can be connected as O2 by connecting this end to this point of the secondary to this point of the primary. So we have this point here, and then of course we have this total winding of the secondary, which is this now with n is number of turns. So our primary is this with supplied voltage B sub P, but our B sub is now would be from is measured from this point, common point of the primary and the secondary, up to this point of the secondary winding. So this is now our connection. Still we have IP going down to the primary winding, and then I sub is going up or going up to this. So that is how we can connect an ordinary two-winding transformer into an auto transformer. Still, the transformation ratio would be the same as in the previous case, except that the secondary voltage in this case is now raised to a much higher voltage than the voltage rating of the secondary here, because the voltage of the primary winding adds up to the voltage of the secondary winding. So the total voltage V sub S would be the sum of the primary voltage here plus the voltage of the secondary winding. So we have the total, and the primary voltage remains the same as V sub P. So in other words, the voltage of the secondary is increased by the amount of voltage impressed to the primary. Now for three-phase auto transformer, we have a connection diagram like this. We have the main windings for the three-phase auto transformer, and since for auto transformer we just make a tap along the winding, so our secondary is obtained from this tap and it's brought out, and then for this winding this tap brought out, and also for this being brought out. So we have a three-phase at the primary, and then also we have a three-phase at the secondary. For example, the primary voltage line to line is 138 kV, then the secondary voltage along the at the secondary is 69 kV. Now in this case we have a tertiary winding which is different or not part of the main windings of our three-phase auto transformer. The third winding is connected delta, and its voltage is 13.8 kV. Now this kind of connection is suitable for substations where our substation needs utilization voltage for its power supply, for the equipment, and for the meters or relays. So we need a lower voltage where we can transform this into 220 or 240 using a step down transformer. So our transformation ratio A, which is defined as the primary line to neutral voltage over the secondary line to neutral voltage, and for Y, our line to neutral is just equal to the line to line over the square root of 3. So similarly for the secondary, so square root of 3 will just cancel, so the transformation ratio is just equal to BP line to line over BS line to line. So let's continue. We now consider circuit model for a three-phase three-winding transformer. Now this time, this is not an auto transformer but an ordinary three-phase transformer, because we do not have a continuous winding for the primary and the secondary, but we have separate windings for the primary and separate windings for the secondary, and another separate windings for the tertiary. Now if we consider the connection here to be YY, then the connection would be this. Considering the polarity again, the each toes of these windings will be connected together to form a neutral here, and for the secondary, the X toes terminals will be connected together to form a neutral here, and then our primary supply will be taken at the H1 terminals, and our supply to the load will be taken at the X1's arcade terminals. So we have the equivalent impedance, okay, between the primary and the secondary by obtaining or by conducting a short circuit, okay, at the secondary, while the tertiary winding is open, and the equivalent impedance, okay, will be measured at the primary, just like when conducting short circuit test for single phase transformers, where we have to short circuit the secondary winding, and then the meters are placed at the primary winding, and then okay, from the values of the voltage and the current flowing, when the secondary winding current is the rated current, then an equivalent impedance will be obtained. So similarly for the three-phase three-winding transformer, we do the same, conducting a short circuit test. No, so in this case, we obtained okay the equivalent impedance between the primary and the secondary. Now another short circuit test shall be conducted by opening the secondary circuit or secondary winding while short circuiting the tertiary winding, and again the measurements of the currents and short circuit currents okay, will be at the primary. So the equivalent impedance that we obtain here is the ZPT, no? The equivalent impedance between the primary and the tertiary. And the third impedance will be between the secondary and the tertiary. Now this time it is the primary winding that is open, while the tertiary winding is short-circuited, and the measurements of the currents and the short-circuit current will be at the secondary circuit. So the equivalent impedance that we can obtain here is the impedance between the secondary terminal and the tertiary terminal, or ZST. Now in this three impedances measured in ohms, okay, and referred to the voltage of one of the windings, then we can just write okay the equivalent impedance ZPS equal to Z sub P plus Z sub is, no? So meaning if we take the impedance ZPS will just be the sum of the primary impedance plus the secondary impedance, while ZPT would be equal to the sum of the primary impedance Z sub P and the tertiary impedance Z sub T, and ZST will be equal to the sum of the secondary impedance and the tertiary impedance Z sub T. So when you want to get the individual impedances okay, for each side of the transformer, so C sub P, now when we solve this, C sub P then would just be equal to 1/2 of the sum of ZPS plus ZPT minus ZST. So as we can see, we are looking for Z sub P, and what we do is just add the impedances with P. So we have ZPS and ZPT, and then we subtract the impedance which does not have subscript P. So we subtract ZST. Now similarly for Z sub S, this is equal to 1/2 of okay the impedances with S. So we have ZPS then plus ZST minus ZPT. And lastly for the tertiary impedance, this is equal to 1/2 of the sum of okay the impedances with T. So we have ZPT minus plus Z is T, then we subtract, okay, Cp is. Now, the impedances of the windings are connected in star, not to represent, okay, the single phase equivalent circuit of the 3-winding transformer with magnetizing current, okay, neglected. So this is now our equivalent circuit for our 3-winding 3-phase transformers, where we have a primary terminal P, secondary terminal S, and tertiary terminal T with their corresponding impedances. Now we have here an example where we have a 3-winding transformer with impedances, okay, Z sub P, Z sub S, and Z sub T, which is supplied with power at its primary with a 3-phase synchronous motor connected to the secondary and a 3-phase resistive load connected to the tertiary. Now, if we have to draw the impedance diagram, okay, per phase, okay, our circuit would look like this. No? The primary is connected to the voltage source, where we have for considering phase A, so we have generated voltage here is sub A, and it is where our primary terminal is connected to, and then our secondary terminal Z sub is connected to our synchronous motor with reactance XSM, and is okay, counter electromotive force, okay, EAM. We neglected, or the resistance of the synchronous motor is neglected in this instance, while our tertiary terminal is connected to a resistive load represented by R. Okay, now we go to the transmission lines. Now, from our study of transmission lines, our transmission lines can be represented either by its T equivalent circuit or by its pi equivalent, okay, circuit. Now, in the T equivalent circuit, okay, what we do is, okay, we obtain the total impedance of the line, okay, by multiplying the unit impedance, okay, by the total length of the line, so we get the total Z, and we divide it by 2 and place it at the arms of our T equivalent circuit. And since our transmission line has also capacitance, so we have here an admittance Y. Even if the capacitance of the line is distributed throughout the length of the transmission line, yet in this equivalent circuit, we lump the admittance together and place it at the middle. And so at the sending end, we have BSN, line to neutral voltage, and then we have the sending end current I sub S. And at the receiving end of the line, we have, okay, VRN as our terminal voltage here, and if we have a load connected here, then receiving current IR will flow. Now, in the pi equivalent circuit, okay, what we do is the total impedance of the line is placed, okay, along here, and the admittance Y, total admittance Y, is divided into 2, and each half is placed at the ends of the line. So half of the Y is placed at the sending end, while another half is placed at the receiving end.